Hi, and welcome to the Consulting Specifying Engineer webcast, Specifying Transfer Switch Controls, sponsored by Cummins. I'm your moderator, Gary Cohen. Happy to join you today on behalf of Consulting Specifying Engineer and CFP Media and Technology. So we'll start off with some tips and tricks to help you guys get the most from today's webcast. If you're experiencing issues with your slides or audio, simply refresh your browser or click the refresh button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast platform. If you're having technical problems with the audio or the slide presentation, just click on the question mark at the top right corner of your screen to access a list of system checks to try. But if you do actually need a technician, just type a message in that Ask a Question box and the tech team will get to you as quickly as possible. Individual user experience questions will be answered, also in that answered questions box. Please type any question for the speaker in the Ask a Question box on the left-hand side of your screen. The live Q&A session will start in about 45 minutes. Today's webcast is being recorded, and you will receive an email within a week with a link to the on-demand event. Finally, to download a certificate of completion and a PDF copy of the presentation, just use the Event Resources tab on the left-hand side of your screen. Those documents will also be available with the on-demand version of this webcast. Now we're going to hear from the sponsor of today's webcast, Cummins. At the conclusion of this video, you may experience a few seconds of silence. That's just to compensate for the varied internet speeds. Please stay tuned. After that, video for today's presentation. Thanks. All right, now we get to the fun part where you can stop listening to me and start listening to someone much smarter than me. I'm happy to introduce today's presenter, Hassan Obaid. Hassan Obaid is a senior global technical advisor, energy management solutions at Cummins Power Generation, focusing on technical vision, business strategy, and solving a wide array of complex problems. Hassan has been with Cummins since 2007 in a variety of roles: power systems design engineering, project engineering, and applications engineering. He's designed power systems involving switchgear, controls, paralleling, transfer switches, generator sets, microgrid systems, and digital solutions. He's developed and conducted technical power seminars on several topics and products involving paralleling, grounding, power systems, and controls. Hassan received his bachelor's degree in computer science and master's degree in electrical engineering from Minnesota State University, Mankato. Thank you so much for joining us today, Hassan. I'm going to flip this slide and turn things right over to you.
Thank you, Gary. And I'm also very excited to talk about transfer switch controls today. As Gary said, you will have access to all the slides in PDF format. So this is just a quick map with contact information of our application engineers in the field. So feel free to reach out to any one of them, depending on your location. They can help you with sizing a transfer switch or even sizing a generator set, or even any other aspects of an integrated power system. So this is just for your reference. Before we start, we have to cover a disclaimer, so I have to read this verbatim. The views and opinions expressed in this course shall not be considered the official position of any regulatory organization and shall not be considered to be nor be relied upon as a formal interpretation. Participants are encouraged to refer to the entire text of all reference documents. In addition, when in doubt, please always reach out to your authority having jurisdictions, or the AHJ. With that out of the way, now we can turn into our course for today, which is specifying transfer switch controls. A critical component of a transfer switch is the control. So this course dives into the features that a transfer switch control must include to meet the demands and complexities of today's applications. And because transfer switch equipment is available in a variety of types with a wide array of features, selecting the appropriate transfer switch for a specific application will require us to have a good understanding of the site needs, the application requirements, and even application restraints so that we can specify the right transfer switch with the right feature to meet the application needs. So hopefully after I finish this course, you'll be able to describe the basic components of transfer switch equipment, discuss transfer switch controls and features to best meet the application needs, and learn about the basic operation of a transfer switch and the transition types. And we've received a lot of questions for this, so I tailored the content for the questions that we received, and there'll be some bonus slides at the end to talk about the withstand and closing rating. So because I saw a lot of questions that came in about the AIC rating, WCR rating. So we'll just spend a few minutes on that topic at the end. I always like to start with the basic pieces of the puzzle that we can put together to build an integrated system, right? So on one side, we have the sources. So that would be your utility, your backup generator, or you might now have renewable sources, wind, solar, or storage. And then we might have in the system power transfer equipment, right? Or commonly known as transfer switches. You might have distribution boards and system level controls. For distribution boards, the most common name that you use in the industry is switchgear, and switchgear falls into UL 1558, and typically that's designed to handle fault current for up to 30 cycles because it also contains a UL 1066 power circuit breakers. So we can adjust that time delay to allow downstream circuit breakers to isolate the fault and enable better selective coordination. You might, or the other name is switchboard, which is UL 891, and that's typically designed and built and tested for a short circuit for up to 3 cycles and can go up to 100,000 or 150,000 amps of fault current capability. And we might have a system level control depending on how big and how complex our system is to manage and orchestrate that entire show. And then we have some kind of a remote monitoring system to do diagnostics, gives us compliance reports, push notifications. In that way, if there's any sort of a problem or trouble in the equipment, we can notify the right technician, and also have them equipped with the right tool to arrive to the site and troubleshoot and solve the problem. Now, the focus obviously for today is only the transfer switch. Now, your application might have any of these, all of them, or you might just have a genset and a transfer switch. You might have 30 generators and 90 sections of switch gear, or you might have something in between as well. So for us, we'll just focus on the transfer switch. So some of the things when you're specifying a transfer switch that you want to check off your list is, okay, first we want to know the application, right? Is this a utility to gen, gen to gen, or utility to utility? And I'll describe that later here down the road. Is this a service entrance or a non-service entrance? For service entrance, you'll have a circuit breaker in there where a fire marshal can come and kill the power for the entire facility if needs to be from that location. The switch type, is this a transfer switch or a bypass isolation transfer switch? And then what is the transition type? We'll be covering the transition type today, open, closed, non-automatic, and what's the difference between all of them. The number of poles, 3-pole or 4-pole. We can spend an entire presentation or entire hour describing the differences between the two and when you need one over the other. So if you have interest in that, please let us know. And then the switch position, is this a 3-position or a 2-position? The focus for us today will be 3-position. We'll highlight the value of a 3-position transfer switch. Cable sizes and entry, top, bottom, sides, where this is going to be installed. Is this going to be in Florida? Is this going to be in Alaska? Is this going to be somewhere else? Is it indoor, outdoor? And the reason is we'll drive different requirements for the environment, right? And obviously you have to have the voltage and frequency, obviously 60 hertz, and then the voltage, this goes without saying, you put that on the one-line diagram and the current rating. And we also need to specify some level of fault current capability, and it's known as the WCR, the withstand and closing rating for the transfer switch. Selective coordination, honestly, is also derived from that fault current capability, the withstand and closing rating. And then obviously the codes and standards. What are codes and standards that are involved with this? Do we need OSHPD, IBC, NEMA, NFPA 110, CSA, or UL? Those are not in any particular order, so you might want to start with codes, but obviously these are the things that you want to think about when you're specifying the transfer switch. So look, data centers, hospitals, factories, and a wide range of other commercial, industrial, and institutional facilities that require continuous or near continuous uptime typically utilize an emergency power source, such as a generator set, when the normal power source is unavailable. And they also have a transfer switch, which is at the heart of this power system. And the transfer switches are responsible for quickly and safely transitioning the load from the failed source, for example, the utility, to the emergency power source, and then transfer it back when the normal power source is restored. And these actions are controlled by the transfer switch control, and this is what we're going to talk about today. Transfer switch, by the way, for codes and standards, transfer switches are tested and designed to the highest standard in the industry, UL 1008. And UL 1008 is harmonized with the Canadian standard CSA, and then it's also harmonized with the Mexican standard, Annex standard. And there's just a little minor variations, but it is the leading standard for safety for transfer switch equipment. Okay, so transfer switch by segment, I couldn't think of a better term, so it's by segment or by application. So if I were to describe this, we'll have a basic control, we have a mid-range control, and an advanced control. And I classified those by application or by segment as for home and small business. And then you have a basic control. So what do we need for that? As a minimum, across all of them, we need to have an ability to start and stop the generator. So for your home and small business, you might have just a single office, or your house, you'll have a basic LCD display. It will definitely be a delayed transition. You're not going to have a close transition for your cabin if you have a transfer switch there. Obviously to have some kind of a basic log event, right? If there's a fault, transfer switch failed to open, failed to close, some other issues, we need to have minimum of some faults enunciated for the operator or the owner. Obviously, some time delays, that has to be in the transfer switch control as a minimum, and maybe some basic transfer switch scheduler so that you can test this regularly, right? And then some level of protection. Now, if we go to the mid-range, and probably sometimes you might notice it's not a clear cut how I have a line in here, and this is going to say this is exactly where it's going to fit, right? So you might have kind of a blend in between the two, so it depends on the application. Again, so for the commercial and light industrial, you'll have more advanced features, so maybe advanced time delays, more ability to do scheduling, a higher level of protection, because you might do operations with the utility, maybe close transition. You'll have a different LCD screen, better, more richer LCD screen. And obviously, as a minimum, we need to be able to start and stop the generator. Now, if we go all the way to the other end, the mission critical, we definitely need to have some sort of advanced controls, right? This is our applications are getting more complex, so we need to meet those demands. You'll have, for example, closed, delayed, and in-phase transition. So the controller needs to control that. Advanced time delays, advanced level of protection, multiple communication protocols to communicate to the different aspects of your SCADA or BMS, advanced digital IOs, load metering. You might need to have a sophisticated colored screen to give you more information, richer information for your operator or for the service technician or even for the owner of the facility. A lot of you have also mentioned in the past when I presented to the consultant engineers, they said, okay, well, between mission critical, but we also have what's called enhanced industrial or enhanced commercial. Where does that fit? Well, that fits in the category in here as well. So those features for the advanced controls, they kind of go into the mission critical and the enhanced and industrial, enhanced commercial and enhanced industrial as well. So this is what we're going to cover today, is on that end of the spectrum. So the common transfer switch applications, you've heard the term utility to a generator, and this is 60% or 70% of what you do will be in this category in here. So a utility to generator is you have one generator and one utility. A generator to generator, if you have a prime application, so you'll have two generator sets and the transfer switch switches between the two. And here you will need a little bit more sophisticated control, right? Because it needs to manage the run hours, for example, have two separate start signal to start each one of them. So you'll have more advanced control for this as well. Utility to utility. This is if you have redundant utilities and you have one to transfer between one to the other. And then there's a three-source system. So three-source system, you'll need to have two transfer switches for that. And I didn't label them as generator or a utility because you can have any combination of those. You might have two utilities for source 1 and source 2, and then source 3 is a generator. Or you might have S1 to be the utility and S2 and S3 to be the generator. So this is a three-source system, right? For example, you might have one generator backing up two utilities, or two utilities backing up a generator. It just varies on your application and where you are in the country and what you're specifying. But that's a three-source system, right? So, but it's accomplished using two transfer switches. And they'll communicate with one another what is needed to be done to switch between the appropriate source. So common installation types. Transfer switches are applied in a variety of applications which typically fall into one of those four categories. We don't have time to discuss all the codes and standards here today, so I just picked the NEC and few of those articles for us that are really important. So you have the NEC, which is NFPA 70, right? So you have Article 700, 701, and 708. You're familiar with 700, which is what is essential to life safety during fires and other disasters. And then you have the legal required Article 701. And then you have the COPS 7 Critical Operation Power System, Article 708. And those rules require us to have an electrically operated circuit breaker, right? And so, for 700, 701, 708, we need to make sure that there is an acceptable power at the terminals in about 10 seconds with a 1 second time delay when the preferred source, the utility, is available. And then there's 702, which is there's no bearing to life safety, right? For health and life safety. So you can get away with using a basic transfer switch for here. So again, we just need to understand our application needs and requirements so we specify the right transfer switch with the right features. Okay, so let's start going towards the direction of the transfer switch control. So if I were to think about transfer switch components, if I were to break it up, typically you'll have the mechanism and the control. But I've also added the enclosure and accessories just because we're here to learn, so we can talk about those. So if I were to break it up, I'll say four components: the mechanism, the control, an enclosure, and some accessories. Let's talk about the mechanism. One slide on it. It is a critical component of the transfer switch, right? It's the guts of that transfer switch. It's that mechanism. It has the electrical contacts on it, and those electrical contacts typically are brazed on for a better conductivity and corrosion resistance. And those are where the contacts are brazed on to the switch contact, the switch mechanism itself. You probably can't see them, but here's an example that you can see if you look closely. And there's solenoid operators to open and close the transfer switch. You'll have connection terminals, and the connection terminals are where you bring in the three phases and the neutral, if you have a neutral in this in the application you're using. And then there's arc chutes, and the arc chutes are typically installed in the UL1008 transfer switches close to the contacts to draw that arc away and distinguish the arc. So these plates that you see them staggered in this picture that you have in here. So this is basically what the switch mechanism is and the major components of it. Regarding the enclosure, obviously you can't have just a transfer switch out in the open. It needs to have some kind of an enclosure around it, right? And those are designed to meet certain standards and the typical enclosure types, depending on the environment where this is going to be installed, right? You have a type 1 and type 12 are for indoor. A lot of people think that a type 12 is the highest number. So yes, it has the best protection, but actually type 12 is an indoor application. You can look those up online from the NEMA or from the NEMA website to get more detailed description of exactly the differences between all of them. So type 1 and type 12 are indoor, general purpose, or dust tight, and then 3R for outdoor enclosure, and then 4 is watertight, and then 4X is stainless steel. And then, for example, you might install condensation heaters or some kind of a heater to go inside the transfer switch. It depends if this is where this is installed. Which takes me to the next slide, which is accessories. And some of the accessories that you see on a transfer switch, for example, surge protections, right? And you can have surge protections. We want to have those installed on the line side to protect also the control on the transfer switch. And you might have two. You have one on the line side, on source one, the utility, and then another one on the generator side. So you'll have them two per transfer switch. Protective relays, I'll have 3 slides to talk about that today for closed transition operations. Typically, you might have a 62 PL parallel timer, a 32R reverse power, so that it prevents us from backfeeding the utility, and then an 86 lockout. So if there's a problem, the 32R will trip the utility, will trip the 86 lockout, and then we use the 86 lockout, one of the decks to contacts off of the decks to do things like trip a circuit breaker, do an annunciation, send a BMS signal, whatever you want to do with the 86 lockout. By the way, those numbers are ANSI designation, and you can also look those up as well. You might have a utility grade meter, right, in the transfer switch as an option. Redundant DC power supply. So you might have your own power supply, or use the generator set battery, or you may want to use an independent power supply as well. We talked about a thermostat controlled anti-condensation heater for the cabinet. You can add that as an accessory. Additional aux contact, auxiliary contacts. I'll have one slide to talk about that. Every transfer switch will come with a minimum 2 or some number of aux contacts, but you can have additional contacts as well. Digital inputs and outputs also can be added. So those are some of the features and the accessories that you can add to a transfer switch. Now we've covered all that, we can now finally start talking about transfer switch control, which we're here for today. So the transfer switch control is an essential component of the transfer switch. Some of the high-level feature, it's the human-machine interface. Or the commonly used name is HMI. So HMI stands for human-machine interface. It's what the operator, the owner, the user, the tech will interact with, and they can get normal operation data, alerts, if there's any alert in the system in the transfer switch, source data. It's doing the switching of power, right? Switching commanding the mechanism to switch between one source or the other, or doing the power sensing, so sensing the 3 phases on source 1 and source 2. It can also do load metering, so we don't need to have an additional accessory to do the load metering itself. It might even have automatic downstream load sequencing for some of the applications that you might have. It has built-in you can have protection and communication. And with today's technology, we can take all these things that I've listed in here and package it into a single controller without the need for additional modules for enhanced and better reliability. Okay, so now let's just start diving a little bit more in some of these features, right? So the human-machine interface, right? When I say readily available data, an operator can easily see for this our mission-critical and enhanced industrial, which source is available, source 1 or source 2, or if both are available, which source the transfer switch is connected to, date and time, for example, currently date and time, load, well, how much load is being consumed currently, source 1 and source 2 voltage. Also, It's important if there's any active timers. I've been in a lot of applications where I'm standing in front of the transfer switch and it did not get that information. There's multiple timers, and these timers are staggered. You have a transfer from one source into another. You might have an elevator signal timer. You might have also a program transition timer. And some of these, and all these timers are staggered together. So if you don't get that enunciated on the HMI, the technician might be standing going, okay, what's going on here? Why didn't transfer? So this can be very useful feature to specify this active banner that tells you this information. Or if there is an inhibit signal which an inhibit to prevent the transfer switch from moving from one source into another. Some other information for our mission critical application that is essential is we need to know faults and alarms, right? Or maybe just information that the transfer switch switched from one source into another. And we need to have information such as the fault code name, code description, so that we know, and if what is the error, something happened, what is it, what's the fault code, and like I said, basic information about it, and maybe if we need further information, a technician or the owner or the operator can go investigate the problem further. We also need to have some level of an event history. I've talked to, again, thousands of consultant engineers over the last 10 years, and some of the features that they've requested for their mission critical applications, high-end applications, is some kind of a history for the faults that they see. Fault codes, list all of them. If there's any active time delays, keep that in the history. If there's any test that has taken place, keep that with the time and date. So all of that now can be built into the transfer switch control itself. We may also want to have some level of source statistics. So you have, like again, the transfer switch switches power between source 1 and source 2. We want to, for example, we probably want to keep track of how many times the transfer switch is transferred from the utility onto the generator. This tells us, well, maybe there is a problem with the utility. We need to call the local utility and address some of the issues we're having. How many times the source 1 has failed, like I said, or maybe the generator set has failed to come online. How much time we've spent on either source, last transfer due to a failure, and keep track of this information and what we call source statistics. And we need this for both sources, source 1 and source 2. Again, additional information that would be very beneficial for our facility operators and the owner itself is load data, right? And the load data, for example, it goes beyond just having the voltage and the current, right? This is obviously without saying we need to have that. But we also, for example, want to probably know the power factor, right? So if there's problems with the loads, we may want to have a power factor correction, add a capacitor or do something about it. But we can even go a step further and we can go beyond the current, the total power, the reactive power, and the apparent power when we can do harmonics, right? Well, maybe we have a total harmonic distortion both on the voltage and the current. And we probably want to have, if the percentages are in the higher percent, 3-4%, well, we have a problem in here. And this transfer switch control can tell us or alert the operator, hey, you may want to investigate your load. There's a problem in here. I mean, if you're less than 1%, you're in the 0.5%, so that's pretty healthy. But if you go up 3, 4, 5%, okay. So we might have an issue in here that we need to investigate and solve this problem. And now we can incorporate in the transfer switch control a metering chip that is able to do that functionality without the need for, say, an additional metering equipment to do so, which can add thousands of dollars, right? Exercise function. So hopefully, I think I got a question also from the audience about, well, how much I should exercise the generator and the transfer switch. Typically, you just want to do, I like to use the rule of thumb is the 30-30-30, okay? So, I mean, you should follow what is outlined in the manufacturer's recommendation, but the 30-30-30 is every 30 days for 30 minutes and load up the generator 30%, right? And so the transfer switch can do that function for you in terms of doing that transfer from the utility onto the generator and do a test with load. And so you can do this regular exercise, and you can have built-in multiple exercise schedules with exceptions. So you might say run every month, but don't run on certain holidays. So don't run on Thanksgiving Day, for example. Another important feature that we need to have is the adjustable time delays, right? And there's about 5 or 6 different time delays that need to be in the control. And those time delays I've listed in here, typical time delays of minimum and maximum. I'm sorry, I did not list the typical time delays, but the min and max. So you can go between 0 and say 3600 seconds in here. So you have the engine start, right? And then there's the engine time delay. The time delay is the cool down time delay. This varies whether you are in the middle of the summer in Arizona or in the dead of winter in somewhere in Alaska or up north. Typically 10 to 15 minutes is good, but again, we have to refer to the manufacturer of the generator set and they give you that information. Transfer time from normal to emergency or the retransfer time delay. So this is going back to the utility. Typically that's set at 30 minutes to make sure that the utility is stable if it comes back. We're going to spend some time talking about the program transition delay, so we'll hold off on that. And there's, elevator signals as well. For security protection, we need to have some level of security on the control itself. So you might have multiple levels of security. We don't want everybody to be able to adjust all the settings. We don't want the owner, I don't know, it's up to you, but one person to have access to everything. We need to be able to have that segregation of levels of users so that we don't mess with the settings. And for example, you have a user level that only view the information, maybe advanced level, you can mess around with some of the settings. You can see all the information, but you can only adjust few settings. And then there's the service where you have all the access to everything. But again, we need to protect that with a password. So we don't have an operator go and change the settings for the closed transition operation. For voltage sensing, so voltage sensing, the transfer switch control needs to be able to sense the voltage on both source 1 and source 2. And what you want to put in your specification is that we want to have 3-phase sensing on both sources. On the source 1, one of the sources could be the utility, right? And then you might lose 1 phase on the utility. If the other one is the generator, typically you're not going to lose 1 source on the generator, but we want to have 3 sources because we don't know when, because of the field, where do you want to connect source 1 and source 2. So you want to put in your specification, you want to have 3-phase sensing both on source 1 and source 2. And obviously, some kind of a loss phase detection, sync checks, we'll talk about that later. We want to be able to monitor both sources and detect when the neutral current exceeds, for example, a certain threshold. That's something that you want to also call out in your specification as well. Okay, so now let's talk a little bit about transfer switch transition types. So the way the load is switched between the 2 sources, again, a transfer switch, you got 2 sources, source 1 and source 2. The way we do that transfer is called the transition type. And I'm going to talk about 3 transition types. I'm going to talk about the automatic, open transition, and automatic hard close transition. Then I'll talk about something called non-automatic transition. The open transition is divided into delayed, fast no sync, or fast no sync, and then fast sync or in phase. So let's talk about all the transition modes right now. So the open delay transition, it is known as break before you make. You break the connection between the 2 sources before you make the connection to the alternate source. And it's a fully automatic, right? And you have an intentional time delay where you transfer between the 2 sources, right? So you're on source 1, you lose power, you don't immediately go to the generator, for example, or the utility if it's a utility to utility. You intentionally wait for a predefined amount of time, which you program in the program transition time delay. You might say, well, why do I need to do that? Well, it depends on your application. If your application is a stored energy load, such as an MRI machine, so it's more capacitive, or maybe an inductive motor, if the motor is connected to source 1 and you lose power, remember that motor is going to spin due to that inertia, and as it spins, when you remove that EMF force, is as it spins, remember it has it has all the windings in it. Now it starts generating power at its terminals. Now it becomes a generator. So if you transfer to an alternate source, and when you close that immediately, you will close a source that is out of sync with that motor. You will not cause damage to the transfer switch, but repeated damage to the inductive loads or that capacitive loads, and over time will cause failure. And so you have to have that predetermined amount of time delay. So you might ask, well, how long do I wait? Well, it's not a problem. You can refer to the NEMA MG1 recommendations. They actually give you a calculator online, but you need to know a lot of information like the time constants, inductance, capacitance, and what so on and so forth. Or they tell you, look, if you have a motor, what you got to do is wait 1.5 times the open circuit time constant, which is typically listed on the inductive loads spec sheets. If they don't have it, they should provide it for you, whoever is providing the motors. And what that does is if we wait that amount of time, that puts the output voltage that gets generated by the load to a safe level. And NEMA dictated that, they told us that, okay, 22%, if we wait that long, that puts that voltage at 22%, and that should be safe level for us. And so this is why you want to specify a 3-position transfer switch. This is why you have to do it. And you might say, okay, well, if you just squint your eyes and look in here, you can see that for a 300 horsepower motor, to get down to 22%, all you have to wait is not even 1.5 seconds. So if you wait 2 or 3 seconds, that's plenty for 300 horsepower. And remember that if you have multiple motors connected on that transfer switch, you don't have to add that time constants of all of them. Just pick the largest one and use it, because remember, all of them are decaying together, right? And you can see for a 50 horsepower or 60 horsepower, I can't read that very clearly here from my screen, that takes less than a second. Again, the advantage also of using a 3-position transfer switch is load shedding, right? The National Electric Code, the NEC, allows the alternate power source to supply emergency, legally required, and optional system loads from the emergency backup source, where if you have adequate capacity or you have selective means to perform load shedding. And to do load shedding, we need an external device such as a system level control or some kind of a load management system to send the transfer switch a shed signal, right? And so this is why we want to specify a 3-position transfer switch. Why? We don't want to shed to a de-energized source. So if you're connected to the emergency backup source and you do shedding, we want to go into the center off position. You're neither connected to any source. You don't want to go to a de-energized utility, because if the utility comes back, it's going to come back momentarily and goes, and that can cause damage to your load, right? Or it might come and goes few times simultaneously or within a few seconds, and that repeated hit to the load can cause damage to it. I do need to pick up my pace a little bit faster, so I have a few more slides to go. Regarding the other 2 transition modes that are open transition, we have the sync, or commonly known as in phase. Again, remember, when I talk about those, I'm talking about 2 live sources. If you have you lose the utility, you don't have a UPS, you have to wait, you're going to be in the dark for the generator to come online, which is typically 8 to 10 seconds, right? So with the open transition sync is that the 2 sources are available. It is, again, break before make. There's no connection between the 2 sources. And this is known as in phase. This happens very fast. We have no time delays. It's just however long it takes for the mechanism to switch between source 1 to the middle to source 3. To source 2. And that's typically 40 to 80 milliseconds. The control monitors and watches when the 2 sources they become in sync, and then it will initiate that transfer immediately. And then, for the open transition sync, typically you want to go with the typical application. Again, small inductive loads, resistive loads for sure. Small inductive loads, anything less than say 20 to 15 horsepower. Or you're going to refer to the NEMA MG1 to give you that exactly how long it, and look at your motor, look at your loads, look at your inductive loads or capacitive loads, stored energy loads, and then derive what is needed, and then use whether you want to have a fast no sync or fast sync or delayed transition. For the open transition no sync, we don't have to have the two sources come in synchronization, and then there's no intentional time delays because the loads is resistive. We don't care if the two sources are in sync or not. We'll just do the transfer immediately once we want to initiate the transfer. Now let's switch gears and talk about hard close transition. For the hard close transition, also known as make before break, we're going to connect the two sources momentarily together before we break that connection. And it's hard close transition because it typically needs to be done within 100 milliseconds. So momentarily the two sources are paralleled and then we break that connection. It is a seamless load transfer. This is the biggest advantage of it. And obviously when you use this a lot if you're doing testing with load or if the utility comes back and you're going from the generator to the utility. When you have close transition operation, you need to have an agreement with the utility. The utilities are not too thrilled about you specifying close transition. They really don't jump on that opportunity and say, yes, I'm going to help you with that right away. Usually they take their sweet time and you want to initiate this process at least 6 months in advance. And it can cost a lot of money, anywhere between $20,000, $30,000 to maybe $100,000. It depends where you are in the country and which utility you're working with. And you need to have that intertie agreement. In some cases, they require to have the 62 parallel timer, which is the transfer switch control has an internal timer to time how long the two sources are connected, and then it commands the mechanism to open. But some utilities, they say, nope, this is perfect, I'm happy, but I'm not too happy about that, but I want to also have an additional parallel timer. So this is an independent component that can be specified for the transfer switch and then add that on. Reverse power, so we don't backfeed the utility, and an 86 lockout. An 86 lockout so that we can trip circuit breakers or send annunciations to a BMS or SCADA system. When it comes to close transition, there are 3 methods for synchronizing. So the synchronizing methods are 3. We have passive, sync by slip frequency, and we have active sync. Passive synchronization, it's basically no sync. You're not really driving any sources to go into synchronization. All you have is a sync check. So you sit and you hope that the generator and the utility will fall into synchronization, maybe for some cosmic event that drive the genset to just nudge a little bit its frequency, and then when the conditions are met, it will do that transfer. Sync by slip, you intentionally set the generator. You can't set the utility to run at 60.1 hertz. You can't do that. But you can set the generator, for example, to run a little faster at 60.1, which is not going to damage the loads. And then every 10 cycles or so, the generator and the utility will fall into sync, and then we can do that close transition. Or we can go into active synchronization. If we go into active sync, remember the transfer switch does not have any synchronizers. The synchronizers are on the generator set. We get an output from the control that drives the generator into synchronization with the utility. So we need kind of an input, PT input from the utility line side into that generator. And then once we need to do that close transition, we'll just say the transfer switch control says, okay, it's time for me to do this close transition. Genset will start synchronizing. Once the sync conditions are met, phase, voltage, and frequency, and this is what you want to have, is if you have close transition, you want to have an active sync, you want to specify phase, voltage, and frequency. There's a white paper that you can refer to that describes why that's needed. The last one I want to talk about is non-automatic transition, and the non-automatic transition is it's a fully break before make. It is very, very similar to the delay transition. However, the transfer is manually initiated. So if you lose power, the generator set will start, but it will sit there and wait for you, the operator, to go and say, okay, go ahead and switch from source 1 to source 2. the advantage of this non-automatic is that, and it's different than a manual transfer switch, is that, and this is in here, all the protection, all the intelligence that I described, everything that led us to slide, whatever, 36 is all in there, right? But the transition is initiated manually. The MTS, which is manual transfer switch, the typical manual transfer switch is a very, very rudimentary transfer switch. It has pretty much no controls in it. It has maybe 2 LED lights or LED lights and a way to switch between source 1 and source 2. That's the kind of the definition or what's accepted in the specifications for a manual transfer switch. So the non-automatic gives us a lot more. And remember that the National Electric Code requires automatic transfer switches for life safety and legal requirements, and so 700, 701, and 708. Downstream automatic load management, some advanced controls in this mission critical or enhanced industrial is that you can have automatic load sequencing. For example, you can drive from the control itself without additional relays or equipment or parts. You connect that to an MCC, for example, and stagger some of the loads. And you can do load add, load, or bring the connect loads add or shed. And again, those are for loads if you have loads connected to that downstream of that transfer switch itself. So some of these features can be built into the control itself to sequence these loads. Another thing is that network communication and protocols, we need to have some kind of a communication from the transfer switch itself for this mission critical applications and enhanced industrial. And as Modbus is typically used, and Modbus can be over RS-45 serial or over TCP/IP. And then we can send this information to some cloud device, to a BMS SCADA, and obviously a remote annunciator as well. We can do all this simultaneously from the advanced control as well. Typical connections, don't use this image in here, probably can't read it, but you can look at from any manufacturer of transfer switch, a standard interconnect diagram to give you this information. You get remote start integrity, inhibit signals, elevator signals, load shed. Those are kind of the typical signals that you want to specify when you specifying a transfer switch. Listed those all in here for you, so use those as a reference. And this takes me now to the summary of the transfer switch control by segment. So we've talked about all these features, right? Everything that led us to slide number 44. All these features now, and the capabilities can all be integrated into a single controller for enhanced reliability, connectivity, and serviceability as well. And this concludes everything that I need to talk about with regarding the transfer switch control. I just want to spend just 2 more minutes, and because a lot of you have asked questions about the withstand and closing rating. Remember, transfer switches have WCR, withstand and closing ratings. They don't have AIC rating. AIC is interrupt ampere capacity. So that's a function of a breaker or a fuse. And the manufacturers list the maximum available fault current at the maximum durations at the maximum voltage. And so you can carry this down voltage-wise and time-wise, but not up. UL 1008 requires us to have a withstand, be able to withstand the fault, and then close onto the fault. So this is what we have at WCR, not an AIC, but a WCR. So pretend that it's just a dot on your SKM or ETAP when you do the calculations, right? Just a dot, and must be able to withstand that fault current for that duration. The WCR can be used, specified using a specific or until the OCPD trips. So you can have a specific breaker or time. Which one is better? Both are great, right? It depends on your application. But a time-based, if we have a high time-based rating, this simplifies the breaker issues that you're always having and coordinating a circuit breaker with a transfer switch, and saves you from having to call the factory and say, does this transfer switch coordinates with this breaker? Well, if I have high WCR, then you can use a breaker of your choice as long as it meets UL standards, UL 489 to be specific, or UL 1066. And so this is the advantage of that. And then the short time demonstrates, if we have a short time rating, which is going beyond the WCR, demonstrates the transfer switch can still carry a rated current. So even if it experiences a fault, it can still be used in the circuit in your application. And obviously this can simplify selective coordinations, but you want to pair it, this short time, with a 1558 switchgear ahead of it. And that's it. And this takes me to the course summary. I hope this was beneficial for you today. So in conclusion, transfer switch typical components are the mechanism, control, enclosure, and accessories. The controls for transfer switch can come in a wide range of features and capabilities. Mission critical, industrial, enhanced commercial application really requires this sophisticated, capable controls. Write specifications based on features and functions. And to help you with that, you can use the AIA master spec. These are all hot links that you can go to the AIA master spec and just copy that information from there. There's also, here's some initial resources, a few white papers that we've listed for you on specifying a transfer switch, close transition as well. And there's few power hours those are hot links. And then if you want more information about how to learn more about the WCR and the transfer switch time durations, you can also visit the CSE webcasts. Sorry, this took me a little bit, 5 more minutes than what I have planned, and now I'll turn it over to Gary.
So now Hassan is going to answer some questions from the audience. Just type your questions for the presenter in the Ask a Question box on your screen. We'll get to as many as time allows, although I just wasted a little of your time. Questions that we don't get to today will be posted online at www.csemag.com. And remember to download a certificate of completion or a copy of the presentation. Use the Event Resources tab on the left-hand side of your screen. Hassan, let's jump into a few of these questions before our time runs out here.
Sure.
To start off, what is the language required when sequencing the controls of a transfer switch in bid documents and specifications?
That's a great question. I talked about that in the previous slide. So the AIA spec, that 3600, lists exactly what language you need to use. You can copy and paste, and again, it's the AIA master spec, follows that specification format, makes it easy for you. List all the information regarding the control or the mechanism itself, or the operation, even including close transition, open transition, service entrance, non-service entrance. All that should be highlighted in the specification on the master spec.
Got it. Is there a standard for integration with elevators?
Okay, good question. Not that I know of. I haven't come across a standard, no NFPA or a CSA or any NEC standard for elevator signal for integration with an elevator. But what you want to do is you want to make sure that there is an elevator time delays in the control itself, and with flexibility to adjust those time delays, so that it allows, if you're doing testing, for example, is to allow that elevator to come to a certain floor, to communicate between the elevator controller and the transfer switch, and allow it to come to a floor level, and then open the doors. So what you want to do is make sure that the transfer switch control has those time delays in them.
Got it. What should be specified to get the best level of short circuit performance available?
Okay, so for the short circuit, that's a really good question. What you want to do is you want to do the calculations, right? Do your calculation to the best you can. And we know this is not easy. You don't have all the information. So do your calculations and then figure out what is the available fault current at the terminal where the transfer switch is applied. So if you're applying your transfer switch way downstream in the circuit, however, and let's say way upstream, your fault current is, let's just say 200,000, right? But the transfer switch is applied way downstream in the circuit. We don't want to cascade that 200,000 all the way down, right? Obviously. So you want to do where the transfer switch is applied, calculate that fault current, and then use the WCR, right? So when you use the WCR, the withstand and closing rating, match that. And then, for example, you can take advantage of this high time duration and then you can select the breaker of your choice to protect the transfer switch. Remember, transfer switches are not designed to break a circuit, to open up, right? We don't want those contacts to open if there's a fault. They should remain closed if there's a fault. We want the breaker ahead of them to break the circuit. So the transfer switches must be protected by a circuit breaker upstream.
Got it. So about 5 minutes.
Sorry, go ahead.
Oh, go ahead.
Yeah, a breaker or a fuse, but the breaker obviously gives us more. A breaker or a fuse, but the breaker gives us more flexibility in terms of resetting it or whatever if there's a fault.
Got it. We got about 5 minutes left. We'll get to a couple more questions here. Is it possible to use half-size circuit breakers in an ATS, assuming the ampacity will not be exceeded? Is there another method of adding more circuits, again, not exceeding the ampacity of the ATS?
I don't know what's meant by a half-size breaker. I'm guessing maybe a half cycle, like or 1.5. Did I hear 1.5, or maybe 1.5 cycles? So didn't get that part exactly, but 1.5 cycle. If you specify, if the transfer switch is designed to handle, let's say, 100,000 amps at 600 volts AC for for 0.05 seconds, which is 50 millisecond. At 60 hertz here for us in North America, that will be 3 cycles. That should also cover your 1.5 cycles, right? Because if I can handle 100,000 amps for 3 cycles, I can definitely handle more than 100,000 amps or 100,000 amps for sure for this 1.5 cycles. So I think this is what the question was asking. But if not, please send it again, and I'll be happy to address it on the CSC's website.
Perfect. What are the best strategies to ensure the health and readiness of ATS?
Great question. I mean, you obviously want to do this monthly testing, right? It's required by code for certain applications. Refer to the manufacturer's recommendations for testing, for inspection. Usually any manufacturer of a transfer switch, they have the operator manual, the service manual. They have a checklist for you to go through. So have that handy. Privacy, not you as a consultant, but the operator, the facility owner and the facility operator, and possibly the owner, they need to have access to that information, and they'll be able to just go down through that checklist.
Excellent. Can you provide details on specific equipment requirements upstream from transfer switches and control requirements? Okay, so upstream of the transfer switch, regarding the distribution board, you just want to make sure, I mean, you can have a 1558, UL 1558 switch gear. And remember, 1558 has UL 1066 breakers, those are power circuit breakers. They can hold the circuit fault for up to 30 cycles. If you do that, then you want to make sure that make sure everything between it and the transfer switch, the cables can handle that fault current. And then you want to specify a short time rating on the transfer switch. If it's a UL 891 board, you have 489 breakers. Those are designed to trip in 3 cycles or faster for 400 amp and above, and the whole board is probably only tested for 3 cycles. So you can get away with a 0.05 seconds or 3 cycles. In terms of control, it just really depends, right? The transfer switch, the minimum control is we need to do start, stop, and then communication. It just depends on the complexity of and the application needs. But for me, what I want to address in here, the power requirements. It's if I have a switch gear or a switchboard, make sure that those are paired with the right transfer switch capability, because that's essential. Makes sense. Unfortunately, that's all we have time for today. So thank you, everyone, for all the great questions. And thanks again to our speaker, Hassan Obaid, for sharing his time and expertise. Thanks so much, Hassan.
Thank you so much. I appreciate it.
I'd also like to extend a special thanks to the sponsor, Cummins, for sponsoring today's event. Now that we're just about done, we do want to hear how we did. An exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it because we use this information to improve these webcasts. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, I'd like to thank you for attending. This is the end of the webcast. Thank you and goodbye.